Hi everyone, welcome to a YouTube demonstration video for how to apply natural ventilation to your building models. Natural ventilation is using the opening and closing of windows to allow cold air at strategic times into your building to help cool it, to keep temperatures comfortable. Um, so in this model, I have set up a window to wall ratio of 20% on all sides currently. And I'm going to just run this baseline condition just to show you where my starting point is at. So this is for Spokane. Um, there's no heating and cooling system. So this is just my starting point. And going to export this to Excel. So these are my results. And if I come here into the duration of the year, the indoor temperatures are in these ranges. You can see that for the majority of the year, 51.5%, my indoor temperatures are less than 60 degrees. So it is cold throughout the year. The first design strategy that I want to implement here is not passive cooling with natural ventilation, but I'm actually going to implement passive heating. So I'm going to come back to my model. I'm going to turn this off. And I'm actually going to do two passive design strategies for passive heating. I'm going to increase the southern window to wall ratio. So I'm going to double left click in the canvas and type 0.6 and come over here where I'm setting my apertures by ratio and make the south 60%. So this is going to allow southern sunlight in the wintertime to come into my building. And as we know, in the summer or in the winter time, the solar radiation hits the south facade more than other facades, other oriented facades. So it is beneficial to have a higher window to wall ratio on the southern facade for that reason, for passive heating. Another strategy I'm going to implement is increasing the solar heat gain coefficient. So I have this group of components here that hopefully looks familiar to you. This is setting a new window construction. So this sets a new window material. I have my U factor here of 0.36, and I have a solar heat gain coefficient of 0.6. If I come over here to where I set my construction, I can see that I'm using the deconstruct construction set, which is under Honeybee Energy Constructions, deconstruct construction set. You can plug in your construction set there. And I plugged in a panel to the window. You can see that the starting point was a U factor of 0.36 and a solar heat gain coefficient of 0.36. This is the construction set. This is defining all of the assemblies in our energy model that go into our Honeybee rooms, aka thermal zones, also known as thermal zones, that we're applying to this energy model. But here, I've set up a way to increase the solar heat gain coefficient from the original 0.36 to 0.6, meaning that there's going to be more solar energy coming in because this is a bigger number. The U factor, I'm keeping the same. Okay, so this component, you can bring in rooms to it. So I'm going to grab them from my apertures by ratio and then bring it into my workflow here. So now this is applying the new window construction and passing it on. So the Honeybee rooms coming out of this output have this new solar heat gain coefficient applied to them. Okay, so now I have this all set up for passive heating. Let's see what happens if I run this. So hopefully the percentage of time that the indoor temperatures are less than 60 degrees goes down because now I'm heating with the sun. And if I come here to the simulation number and export this, I'll see that, yeah, my heating did go down from 51%, or sorry, not my heating, my percentage of time that the indoor temperature is less than 60 degrees Fahrenheit did go down. So it's more comfortable. but that didn't really, I guess I shouldn't have said it's more comfortable. It didn't translate into percentage of time kind of in this range, which is our expanded comfort zone. It translated into overheating. So now we're letting in too much heat. One way we can combat this is now use passive cooling to get rid of this excess heat that we're generating. Because we like this, we like reducing the hours less than 60 degrees Fahrenheit, or the duration of year less than 60 degrees Fahrenheit, but now we've created this problem where it's getting too hot. So let's see if we can use natural ventilation to reduce this percentage up here. So to set up the natural ventilation, we have to come over here where we create our apertures by ratio, and we have to tell the energy model that the windows are operable. That's the first step, and you can just double left click and get a Boolean toggle, and the default is set to false. We can change it to true. Oops, I'm gonna tell my energy model not to run anymore. So it's set to true, to run, or to, yes, to allow for operable windows. This doesn't actually set up the natural ventilation though. It just tells the model that these windows could be operable, but we need to tell the model when to open the windows and when to close them. So the way that we do that is, I'm going to make some space here. We have to put in some parameters for the window and closing controls, and that's under Honeybee Energy Loads window opening, Honeybee window opening. So if you connect that into your workflow, into this flow of parameters, and zoom into it, you'll see that it needs this Honeybee ventilation control to run. This is the only thing it needs to run. There's some default values being assigned here for the fraction of area that is operable, that is actually moving. That's set to 50% as a starting point. The fraction of height that is operable, the distance from the bottom of the window to the top that is operable. The default is set to 1. That's typical of windows that slide horizontally. The discharge coefficient, which is a value that estimates how obstructed the windows are, and it's set to 0.45 for unobstructed windows with an insect screen. So you're basically kind of modeling an insect screen, which is fine. And then window cross ventilation, that's set to false. It's assuming that you don't have cross ventilation set up, and that it's just one-sided ventilation, which is a fair assumption because we don't know what the interior of this building looks like. We've only modeled the exterior, and we don't know if these windows are blocked by interior walls and if there's actually cross ventilation going on. So let's just leave the other default assumptions as they are. The only thing we need is this ventilation control. So go to Honeybee Energy, Loads, Honeybee Ventilation Control to set up the ventilation control. And you need a few things. These ventilation controls are indoor and outdoor, min and max temperatures at which the windows will open and close. I would recommend setting it up this way, but you can definitely play around with these different values. I would recommend setting up the minimum indoor temperature. So let's do that. So I'm gonna type in here, let's do 68 for that. 68 degrees Fahrenheit. This, if you hover over it, it says that it needs to be in Celsius. So we need to convert from Fahrenheit to Celsius. I'm going to go to Ladybug, Extra. I'm going to go to Ladybug Unit Converter. And I want to go, I'm just going to double left click, type into quotes and say Fahrenheit. That's my from units. And then double left click, quotes, Celsius, and that's my 2 units. And make sure you don't have any spaces or anything in there, or else this won't run. And then the value coming out of here is the converted value. So let's make that our min temperature. What this means is anytime the indoor temperature is less than 68 degrees Fahrenheit, the windows will close. And this is important because we don't want to have the windows open when the indoor temperature is too cold, because then we could potentially be bringing in cold air. Like imagine the indoor temperature is 67, and the outdoor temperature is 60, and the windows are open, then we would be bringing in cold air, and it would just be making it too cold inside. So we need to tell it close the windows when it's colder than 68 inside, because we don't need natural ventilation at that point. It's already cold enough. It's already comfortable enough. Similarly, I'm going to copy this and paste it. We want to tell it a maximum indoor temperature. So actually, I don't think we need that. Never mind. We don't need this maximum indoor temperature because we want the natural ventilation to occur when it's hot inside, depending on like at all temperatures that it's hot inside. So we just want this minimum, but the maximum indoor doesn't matter. The other one that I want to put in, and feel free to play with these outdoor min and max outdoor temperatures, but the other one that's nice to put in is this delta temperature. I'm going to actually set this to 1. So this is 1 degree. Oh, I'm just going to set it to 1 degree Celsius. Actually, I'm going to set it to 0.5 degrees Celsius. Sorry. So what this is doing, this is a really good one. It is basically telling you can read this description too, it might be helpful. But it's basically saying that ventilation only occurs when the outdoor is colder than the indoors. You can imagine that, and it has to be at least 0.5 degrees Celsius colder than the indoors. You can imagine that this is helpful because you don't want to be bringing in warm air that is warmer outside than the inside if you're in cooling mode. You only want to open the windows when it's colder outside than it is inside. So that's what this delta temperature is. It's going to only open the windows when they are 0.5, when the outside is 0.5 degrees colder than the inside. Once it's the same, once it's like 0.4 degrees colder outside than it is inside, it's going to close the windows, and especially when it's hotter outside than it is inside, that would be a negative delta temperature, it will have the windows closed. So I think these are the only 2 controls that we need. Let's just run this and see what happens. It's always good to play around with the controls, but I think this might be a good one. Let's see what happens. So I'm going to export these results. Yeah, that actually worked really well. Look what happened. We are providing some cooling, maybe when it's not beneficial here. That's what this is telling me, because we went from 40 degrees or 40% of the time less than 60 degrees Fahrenheit inside to 43.8% of the time. So we might be bringing in air cold air when we don't want it. And actually, this percentage went up from 10.4 to 18. So this is telling me that maybe we could tweak the ventilation controls a little bit to make it a little bit more optimal. So let's go back here. Interesting. We could put in a min outdoor temperature. So that would tell the energy model that if it's below a certain temperature outside, I don't want to run, or I don't want the windows to be open because it's too cold. Let's see what happens when we play with that. So I'm gonna copy this, paste this, and let's play with some numbers here. Oops. See if we can get this a little bit better. So let's say maybe if it's less than 60 degrees outside, maybe we can go with, yeah, let's go with 60. If it's less than 60 degrees outside, so if it's in the 50s, we don't want this to operate. So that's our min outdoor temperature for ventilation. We don't want the windows to open because then it'll be too cold outside and we'll be letting cold air in. Okay. Let's play with these controls and see what happens. Let's make this simulation number 3. And okay, this actually works really well. It brought down the percentage of time that the outdoor temperature is less than 60. It brought down the percentage of time that the indoor temperature is between 60 and 65. It increased the time that we're in this range, and it decreased. Look how much we've decreased since this simulation. We've decreased the amount of time that we're in these hotter ranges. So overall, from when we started this exercise, we went from a comfort range um, uh, we went from being in this like kind of optimal comfort range, which is 65 to 78, 24.6 of the time to 36.4 of the time. So we are moving in the right direction. We still have to focus on these two things when the indoor temperature is too cold. And we could do that by looking at the infiltration rate, looking at the insulation values, of our assemblies, the surface to volume ratio, a lot of other things. But natural ventilation really helped us reduce the amount of time that we were in this really hot zone here. So it was effective. Okay, well, I think that's it for this demonstration video. And in the next one I'm going to make, I'm going to demonstrate how to use fans to bring cold air into your building for cooling versus windows.